Welcome to class. In this video, we're going to discuss linear functions and their graphs.
So let's take a look at a table of values and determine if it is linear or not. So when we're taking a look here, we can first notice that our values for our t, or time in this case, are increasing by 1 second every time. So that's a consistent number. And then our d of t is increasing by 83 meters every time. So when we're looking at this, we can say that x and y are both increasing by a constant rate. That does make this a linear table. Now this is what that table of values is going to look like when we graph it. You're going to notice it's a distance versus time graph, and time starts at 0, so we actually have an endpoint. But then as time increases, distance increases by the same amount. This function is d of t equals 83t plus 250. We can see that it's linear when we graph it because, again, it looks like a line and has a constant rate of change. Now, linear functions can be increasing, decreasing, or constant. Increasing means that as you move to the right, y increases. Decreasing means as you move to the right, y decreases. And constant means that as you move to the right, y is constant. So in fact, the names here mean what we think they should mean. And we can also think of this as a positive slope, a negative slope, and a zero slope. So when we're looking at this, a way to write this as a strong definition is f of x equals mx plus b has an increasing function if m is greater than 0. So in other words, it's increasing if the slope is positive. It's a decreasing function if m is less than 0. Or in other words, if the slope is negative. And it's a constant function if the slope is 0. So let's take a look at this picture here. This is how we calculate the slope of a line. Now, we can write this as rise over run, or delta y over delta x. Delta y means the change in y. So that triangle symbol is delta, and it means change in. And delta x means the change in x. To find how much a variable has changed, you're going to subtract the two variations of that variable. So here you're going to have 2 points, x1, y1, and x2, y2. So you want to know how much did your x change, how much did your y change. Notice that y always goes on the top, x always goes on the bottom, and it doesn't matter which of your points is x1, y1, or x2, y2, but what you have to make sure is that you're consistent, that x1 goes with y1, okay? You can't have x1 mixed with y2, okay? So those subscripts should match within a point. Then you're going to be able to calculate your slope by doing y2 minus y1 over x2 minus x1. So let's take a look at the slope of this line. We can think of this as rise over run, or we can think of it as the 2 points using our formula. So let's start by doing rise over run for a minute, okay? So if I think about it that way, I can ask myself, how much did I rise from this point to this point? And I can see that I started at -7 and I ended up at 0. So that's going to be a rise of 7. Then how much did I run going sideways here from 0 to 4 is going to be 4. So my rise is 7. And my run is 4, means I have 7 over 4. And if you're given the graph, rise over run is a perfectly valid way to find the slope. However, if you're not given the graph, or perhaps you're looking at it and you're just having a hard time counting because it's maybe not the best drawn graph, you can also write out the 2 points. So 0, -7 is that first point, and the second point is 4, 0. And then you can use our formula. So m equals y2 is 0, minus y1 is minus -7, over x2 is 4, minus x1 is 0. Now 0 minus -7, that's the same thing as adding. So I have 7 over 4 minus 0 is 4. So you'll notice you get the same answer both times. The other thing I want to point out while we're still on this slide is this point here is also a valid point you could choose to use. However, because it is going to likely be some sort of decimal, maybe like 4.51, you can't be entirely sure that you are thinking of that number correctly. So given that information, I tend to work with the ones that are clearly at a whole number value before I use the ones that have decimals. Now let's talk about point-slope forms of linear equations. These are what you're going to use if you have a point and a slope, hence the name point-slope. So if you know the point x1, y1 that the line goes through, and you also know the slope, you can go straight to using this point-slope form of the line. Y minus y1 equals m times x minus x1. And this is really handy because it's really quick to put it into this format. If you ever need to switch from this format to slope-intercept form, it's also very easy to do that as well. So let's take a look at this example. I can see I have two different points. I can pick whichever one I like. I'll pick -3, 0. And then I also need to know its slope in order to put it into point-slope form. So I can see my rise is 1 and my run is 3. So my slope is 1/3. That means that my point-slope form might have y minus y1, which in this case is 0, equals m, which is 1/3, parentheses, x minus, in this case my x1 is -3. Now, I cannot leave it like this because there's two ways to simplify. And so y minus 0 is really just y. And x minus -3 is x plus 3. So this is what point-slope form for this line looks like, or at least one of them. If I chose to use the point 0, 1 instead, my slope would still be 1/3. But now I would have y minus 1 equals 1/3 times x minus 0. Which really comes out to be y minus 1 equals 1/3 x. This is also a valid form of the point-slope equation for this line because we just used a different point. These are in fact exactly equivalent if you were to distribute the 1/3 in the first equation and you were to move the 1 over in the second equation. So if we're given a graph of a linear function, how do we write its equation? So first we have to find 2 points on the line so that we can use them to calculate the slope. Then we're going to find where the line crosses the y-axis to identify the y-intercept. And then we're going to substitute slope and y-intercept into the slope-intercept form of a line equation. So here you need to know the slope, and then you need to know the y-intercept so that you can put it in the format y equals mx plus b. Remember, slope is m, y-intercept is 0b. So this is one way to do it, and it's the easiest way if given the graph, you can find the y-intercept. You're also welcome to start with point-slope form and go to slope-intercept form. But we'll talk about that more in a little bit. So here I see I have 2 points. I can calculate the slope between them. So m equals y2 minus y1 over x2 minus x1 comes out to be -3 over 4. I can also see that my y-intercept is at the point 0, 7. So that means b equals 7. So the slope-intercept form of this equation is y equals -3 fourths x plus 7. So let's take a look at this one and see if we can't find both the point slope and slope-intercept forms of the equation. Now in this case, I will start with point slope and then I'll turn it into slope-intercept and I'll visually check to see that both work. So I'm going to start by finding 2 points that I know work. So I have 0, 2 and 2, 8. Those are going to be my primary points. So m equals is going to be y2 minus y1 is 8 minus 2 over x2 minus x1, which is 2 minus 0. So this gives me 6 over 2, which is 3. So that's the slope of this line. And then I am also going to, for point slope form, identify one of my points that I like better. So in this case, I'm going to pick 0, 2. I pretty much always pick the one that has a 0 in it, if that's possible. So point slope form of the line is going to be y minus 2 equals 3 times x minus 0. Remember, you can't leave minus 0 because that's considered unsimplified. So x minus 0 is really just x. So that's point slope form, and then slope intercept form is going to be the one where I've isolated the y. To do that, what's really nice about this is all I have to do is add the 2 to both sides from the point slope form. This gives me y equals 3x plus 2. And you can see that the slope is 3 and our y-intercept is at 0, 2. So the 2 here for our b value does make sense given our graph. So we can find both versions of this line without any trouble at all. Now, when we're looking at a linear function and we know its initial value and its rate of change, we should be able to evaluate it at a point. And so when we're looking at a word problem, we should be able to write the function and we should be able to plug everything into it. So Marcus currently has 200 songs in his music collection, and every month he adds 15 new songs. We want to write a formula for the number of songs n in his collection as a function of time t, the number of months. Notice that they do give us the letters that they want us to use here. So n is instead of y and t is instead of x, just as a fun fact. All right, so now we have n of t instead of f of x. He starts with 200 songs in his music collection. That means that our y-intercept is at the point 0, 200. And every month he adds 15 new songs, means that our slope is 15. So we can write this as 15t plus 200. Again, notice I'm using the letter t instead of the letter x because we have a function of time t. Now we want to know how many songs will he own in a year. Now notice t is the number of months. So how many months are in 1 year? Well, that would be 12. So we're finding what is the value of the function when we plug in 12. So we have 15 times 12 plus 200. And 15 times 12 is 180. So when you add that to 200, you'll end up getting 380. Now, this is a word problem, so our answer should be written as a sentence. So it doesn't have to be a very exciting sentence, but he will own 380 songs after a year. And that is how you simplify how you write that. So again, recognize here that when we're looking at how this was set up, f of x is the standard form of how we write it. But in this case, because we were told we had to call it n, it had to be a function of t, we had to change that out. So just be very careful to pay attention to what they're telling you in the word problem. Now, let's say you're given a linear function and we want to graph it by plotting points. You're going to want to come up with some input values, and you're going to evaluate the function at those input values. Then we're going to plot them and connect them on a graph. Now, when we're given, for example, this function f of x equals negative 2/3 x plus 5, we want to find some very simple things to plug in. So I'm going to make a t-chart like this. And the easiest number I can think to plug in is 0. The second easiest number I can think to plug in would be 1. However, if I plug in 1 here, I'm multiplying by negative 2/3. That's going to give me a fraction. I don't actually want that. So I think, okay, what about 2? 2 is still going to give me a fraction. Still not the best thing to graph. 3, on the other hand, will work out just great because it's going to cancel out with the denominator. So in this case, you can plot anything where the x is a multiple of 3 very easily. So I'm going to pick 0 and 3 as my two values. Now f at 0 is negative 2/3 times 0, which is 0, plus 5, which is 5, which should make sense because 0, 5 is our y-intercept, and 5 right here goes with our y-intercept. Let's also plug in 3, so f of 3. Well, negative 2/3 times 3 plus 5, you'll notice the 3's cancel, and that's really negative 2 plus 5, which equals 3. So I know that I need to plot the points 0, 5 and 3, 3 and connect them with a line. And lo and behold, here's what that looks like. Notice that the next x value you would choose to plug in would be 6 because it's also a multiple of 3, which makes it easy to evaluate the function, okay? Now, let's say we want to find the equation of this line. You can see that our y-intercept is 0, 1, and that our rise is 1 and our run is 2. So now we know m is rise over run, which is 1 over 2, and b, it comes from our y-intercept, 0, 1, tells me that b is 1. So easily enough, this equation is y equals 1/2 x plus 1. So again, this is just another way for you to look at it where you're looking at the graph rather than the numbers specifically as an algebra thing. You're looking at it visually. Now, let's say you're given the equation for a linear function and you want to graph it using the y-intercept and the slope instead of plotting points. So in this case, you're going to find the y-intercept, and then you're going to find the slope. You're going to plot the y-intercept, and then you're going to use rise over run to determine at least 2 more points on the line. It helps to do 2 more points because it makes it much easier to draw your line, okay? So in this case, my y-intercept is the point 0, 5, and I'm going to plot that first. Then, because my slope, my rise over run, is negative 2/3, I know I'm going to go down 2 and right 3 between each pair of points. So looking at that, I have my 0, 5 is the first point I've plotted. Always plot your y-intercept first when you know it. And then I went down 2 and right 3. And here's my next point. But again, the instructions want us specifically to go at least 2 additional points. So we're going to go down 2 again and right 3 again to another point. When you connect these dots, you have now graphed the line that was given to us. What do stretches and compressions vertically do to a graph? And what about reflections? So taking a look at this, I want to start off by reminding you that our parent function, if you will, or our basic linear function, is f of x equals x. Okay, so that one right there is the standard function. Now, if you were to multiply that by a number greater than 1, for example, 2 times x or 3 times x, you're going to notice that those graphs are going to get steeper. So the higher the slope, the steeper the line. And so this is considered a vertical stretch. Then if you do a number less than 1, so 1/2 or 1/3, you're going to compress the line, which is going to make it a shallower slope. That's these two here. Now you might say, but these other lines at the bottom here are also less than 1. They are, however, they're also negative, which puts them in their own separate little category. So negative 1/2 is both a compression and a reflection. Negative x is just a reflection, and negative 2x is going to be a stretch and a reflection. A reflection means that we have flipped it over the line y equals 0 in this case, or the x-axis. So looking at 2 examples here, we already know our highlighted one there is the x. When I reflect that over the axis, I'm going to get this one right here, which has a rise of 1 and a run of 1. However, it's going downward, so it's really a rise of -1. And so this negative slope that has the same magnitude looks the same, but has now been reflected over that x-axis. Now, what happens if we are adding or subtracting numbers to the x? Well, every number you add or subtract is going to be a vertical shift. Vertical shifts can be up or down. So if you're adding, it will be a vertical shift upwards. If you're subtracting, it will be a vertical shift downwards. So you'll notice x plus 4 has gone up 4, whereas x minus 4 went down 4. So what does this look like if we start compressing? Let's look at a specific example. In this case, y equals x. So if I have kind of my original graph here, I could have the point 0, 0. I could have the point 2, 2. I could have the point 4, 4. But then if I have x with y equals 1/2 x, then I'm going to have 0, 0, 2, 1, and 4, 2, because I'm literally multiplying each y value by 1/2, which is cutting my y value in half. So you can see that it's literally a half the distance to the blue one as it is to the red one when you're looking at it vertically, okay? So this is a compression by a factor of 1/2. Now, let's say I take that compression with a factor of 1/2 and I shift it down 3 units as well. Well, I'm going to take after the compression what I have, and then I'm going to shift it down 3 units. So notice this is like order of operations. I did the multiplication first. Now I'm going to do the subtraction. So I'm literally going to take each point and I'm going to move it down 1, 2, 3 spots. 1, 2, 3 spots. And this is going to give me the graph of 1/2 x minus 3. So let's go ahead and try this. Pause the video and see if you can match each equation of the linear functions with one of these lines. Okay, so first of all, I want to recognize a couple of different things. I have y-intercepts right here and right here. So the easiest thing for me is to recognize that number 2 here, the green one, has a different y-intercept from everything else. It has a y-intercept at 0, -3. So I know that its equation must have subtracting 3 in it. So graph number 2 must go with B. Then I need to look at the slopes of the lines 1 and 3 and 4 because they all have +3 because their y-intercepts are all at 0, 3. So the thing that's going to differentiate them is going to be their slope. So let's start with 1, the red one. So I'm going to look down here just so it's a little bit further away from the other lines. I can find 2 points that are on that, and I can see I go up 2, right 1. Rise over run, therefore, is 2 over 1, which is 2. So the slope is 2. Well, which of my equations has a slope of 2? Well, that would be A. Now let's take a look at 3. 3 here, I'm going to use these 2 points. They're simple enough. I have rise of 1, run of 2. So that means my slope is 1/2, which aligns with D. Last but not least, we have number 4. Line 4 is the blue one. I'm going to choose these 2 points. Here you can see I go down 2 and right 1. So that's -2 for the rise and 1 for the run. So that gives me a slope of -2. And we can see that it's negative because it's a decreasing line. So that is going to align with answer choice C. So hopefully you got 1, 2, 4, 3 as your answers too. Now you could have also chosen to go ahead and label these equations on the graph directly. It just depends on what your style is. So let's take a look at this equation here, y equals 5. What's special about this? Well, hopefully you said it's a horizontal line, and that would be correct. It's also known as a constant function because the y value is constant. Now this wants to know what is the y-intercept, and that's pretty easy to see because it's intersecting with the y-axis, and that's at 0, 5. It also wants to know where's the x-intercept, and you can see that this does not intersect the x-axis at all, so there is none. So notice here that not all linear functions are going to have both an x and a y-intercept. Now let's try and find the x-intercept of a slanted line. In this case, we can see that our line intersects the x-axis right here, which is at the point 6, 0. So again, if it crosses the x-axis, it should be pretty simple to see. However, if it doesn't cross at a whole number, doing it by the graph may not be the easiest way. So let's take a look at this one here. This is a horizontal line, and it's given the function f of x equals 2. Notice that no matter what your x is, your y is going to be 2. Again, this is called a constant function, and it is defined by y equals 2 or f of x equals 2 because it does not change. Similarly, if you're looking at a vertical line, you're going to notice x is 2 everywhere on this line, no matter what your y value is. So since x is 2 everywhere, the equation for this is x equals 2. So vertical lines are x equals, horizontal lines are y equals, or f of x equals. So this is something that you want to make sure you know the difference of. You should be able to tell just looking at an equation whether it is horizontal, vertical, or is slanted. Notice that it will be slanted if it has both f of x and x. So let's take a look at this one. Think in your head for a moment, how could I write the equation of this line? Well, it's a horizontal line, so it has to be f of x or y equals. Notice that we're going to use function notation more often than we use y equals. Okay, and what is y everywhere? Well, y is 4 at all the points, so we have f of x equals 4. In this case, we have a vertical line. Think real hard about what that equation would look like. Since it's vertical, we're going to have x equals. And here you can see that this is the value of 7, 7, 7. So x equals 7. Now, one thing I'll point out here is we really don't want to label this with an f. Why don't we want to label it with an f? Well, the reason why is because it's not a function. And we'll talk more about why it's not a function later, but we won't use f of x. It's literally just x equals 7. Now, lines can be parallel, they can be perpendicular, or they could be neither. So let's talk about how we know if two lines are parallel. First of all, parallel lines are ones that never intersect, no matter how far you extend them. And when that happens, it'll be because their slopes are the same. So M1 would have to equal M2. So the slopes of each line would have to be exactly the same. On the other hand, if the two lines create a 90-degree angle or are perpendicular, then we know their slopes are going to be negative reciprocals. So M1 times M2 equals -1 is one way to think about that. Or you can think of it as the second slope is -1 over the first slope. Now, in this case, for example, let's say I give you a slope of 3. A parallel line is going to have the same slope. Okay, its second slope is going to be 3. A perpendicular line is going to have the negative reciprocal. Well, the negative reciprocal of 3 is -1 over 3. What if I gave you an initial slope of 2/5? Actually, let's do -2/5. Well, then the parallel slope will also be -2/5. But the perpendicular slope, you're going to flip the fraction upside down and change the sign. So -2/5 becomes +5/2 because you've, again, flipped it and changed the sign. So looking at this here, are these lines parallel? Well, they certainly look parallel, but can we confirm it? Well, sure we can. So what we're going to do is we're going to find just 2 points that work on one line. And I'm going to pick these two here. And I can say that my rise is going to be -6, and my run is going to be 4. Okay, well, let's find 2 points on the other line. I have this one, and you can see my rise is -6, and my run is 4. So they have the same slope. So you can confirm that they are indeed parallel. You have to recognize that sometimes 2 lines will look really close to each other, but aren't exactly parallel. So always double check. Here we can see we have perpendicular lines, partially because they've highlighted that for us. They told us that there's a right angle here. But how can we confirm it if they haven't done that for us? Well, again, we're going to look at the 2 slopes. So looking at the blue line first, I have this point and this point. You can see that its slope is going to be 5/1, or 5. And if I look at the red line, I'm going to call that M1, by the way. Red line will have M2. I have these 2 points. I have 1, 0, and 5, -1. Here you can see that my M2 is going to be down 1, right 5. Are 5 and -1/5 negative reciprocals? Why, yes, they are. And if you were to multiply them together, you'd get -1. So we can confirm that this does show 2 perpendicular lines. So here we have a graph, and it's going to show the lines f of x equals 2x plus 3, j of x equals 2x minus 6. Those are parallel. That's the orange and the green one. And we, again, know they're parallel because we can see that their slopes are the same. On the other hand, we can say that g of x equals 1/2 x minus 4 and h of x equals -2x plus 2 are perpendicular because 1/2 and -2 are negative reciprocals. And again, when you look at the graph, the red and the blue lines even look like they're perpendicular. So if you're given the equation of a function and a point through which it passes, can you write the equation of a line parallel to it? Well, sure. If you know the slope of the function and you know a point, you can always go straight to point slope form, or even slope intercept form, depending on what point you're given. So here, let's find a line parallel to the graph f of x equals 3x plus 6 that goes through the point 3, 0. Well, if it's parallel to 3x plus 6, then its slope must match it. So m equals 3, and then we have the point 3, 0. So I'm going to go with point slope form on the line. I'm going to have y minus 0 equals 3 times x minus 3. And remember, minus 0 means nothing, so we get rid of it. So our point slope formula line is y equals 3 times x minus 3. Now, if you wanted to write it as slope intercept instead, you could do y equals 3x minus 9. It's up to you which way you want to do it, unless the question asks for one in particular. So if you look at this, you can see our 2 graphs, when you put them side by side, are clearly parallel. Now, can we find an equation of a line that's perpendicular? Well, of course we can. So first of all, you're going to find the slope of the function, and then you're going to determine the negative reciprocal of the slope. So you take a look at what you're given, you find the new slope based off of that, and you use the point that you know in order to put it into one of our formats. Now, let's say that we want to do this in slope-intercept form directly, okay? So here, our slope is 3 for the given function. That means that our perpendicular line slope is the negative reciprocal of that, is -1/3. So if I want to go straight to a slope-intercept form here, what I'd do is I'd say, okay, f of x equals -1/3 x plus b. Then I could substitute in the point I know. And if you want to write this as y equals, because that's easier for you to visualize, that is fine. So I know x equals 3 and y equals 0. So I could have 0 equals -1/3 times 3 plus b. So 0 equals -1 plus b. I add 1 to both sides, and I get that b equals 1. This tells me that my function is -1/3 x plus 1, because all I've done now is I've substituted in the 1 I just found for b into the b spot. Now, do you have to do it that way? No. You could also have gone straight to point slope form and then turn it into slope intercept form if you like. This is one of those things where it's up to you which way you prefer. Now, when we graph those two things, so f of x equals 3x plus 6, and they went ahead and named our perpendicular line g of x equals negative 1/3 x plus 1, you're going to see that they are indeed perpendicular. Now, let's figure out how can we find points of intersection. Well, intersection points are found whenever the two lines share both an x and a y value. Okay, so in this case, instead of x, we're going to use t, but they should have the same t value when their y values match. So to find a point of intersection, you're going to set the two equations equal to each other. And then you want to solve. So in this case, I'm going to add t to both sides. And that's going to give me 4t minus 4 equals 5. Then I add 4 to both sides. And I have 4t equals 9. Then I divide by 4, and I get t equals 9/4. Now, you might be tempted to box that and be done. However, they want the point of intersection. Because they're asking for the point of intersection, that means we need to know both the t value and the y value. So now I need to substitute that number into one of my equations. Now, which one you plug into is up to you because you will get the same answer both times. Now, I'm going to substitute it into my j of t because I find that's an easier equation. It doesn't require any multiplication. So I have j of 9/4. It knows I'm replacing the t with 9/4 because that's what I'm plugging in, is 5/1 minus 9/4. Now, in order to subtract these, I do need them to have a common denominator. So 5/1 is going to have to get multiplied by 4 on top and bottom. This is going to change it to be 20/4 minus 9/4, which is 11/4. So now I can see that my point of intersection is 9/4, 11/4. And lo and behold, if you were to look at the graph, you would see that that's the point of intersection. However, it is not in your best interest in order to for you to graph these two and then see if you can find the intersection without doing it algebraically, because it would be very difficult to confirm 9/4, 11/4 simply by the visual. So remember, this is definitely one of those ones where you want to use algebra to help you solve. So let's take a look at a word problem example of how we can apply some of these things. A company sells sports helmets. The company incurs a one-time fixed cost for $250,000, and each helmet costs $120 to produce and sells for $140. So the first thing they want us to do is find the cost function to produce the X helmets in dollars. So the cost function we're going to say is C of X, because they've named it C. We know it costs them $120 for every helmet. So we have $120 times X helmets. But they also had a one-time fixed cost of $250,000. Normally, fixed costs come from things like purchasing a piece of equipment or purchasing the factory space in the first place. So that's the sort of thing that we're talking about there. Now, B is the revenue function. Revenue is asking what are we earning when we sell it, okay? So if I sell each of these helmets for $140, how can I write a revenue function? Take a moment, think through how you'd write that. So hopefully you have R of X, because they told us R, is equal to 140 times X. Because for every helmet, you're earning $140, you have to multiply those two numbers together. Then C wants us to find the break-even point. So how many helmets do I have to both make and sell in order for my cost and my revenue to be the same amount? Okay, this is called the break-even point because they are, if you have the same cost and the same revenue, you have zero profit, but you're not losing money. So go ahead, set these two equations equal to each other and solve. And when you're done with that, unpause this video. Okay, so we set them equal to each other. We have 140x equals 120x plus 250,000. We can subtract 120x from both sides, and we get 20x equals 250,000. Then we just have to divide both sides by 20. When I do that, you're going to notice I can cancel a 0. And then I really have 25,000 divided by 2, which is 12,500. So here, I would say that the break-even point, the point at which our cost and revenue are equal, is 12,500 helmets. Anything past that is going to give me some amount of profit. And when you take a look at the graphs here, you can see that my blue line is cost, my red line is revenue. We want to go past the point where revenue is above cost. So pretty much anywhere in this section here is going to be profit. Anything before that is going to be a loss of money. All right, I hope that was helpful for you guys, and I'll see you in the next video.